I mean, a big area of excitement and interest in the community at the moment, as you'll know, is GANs, and Sebastian was telling me a little bit about the workshop just now. But we also thought it would be really good to just have an overview of this whole area. I mean, deep generative learning is supposed to promise so much. We're not sure exactly what it's going to deliver yet, but it seemed like a really good way of starting the symposium day. And Sebastian seemed the perfect person to give a talk. So over to Sebastian to tell us about probabilistic deep learning, a stock take.
Well, thank you very much for the kind introduction, and thanks to the organizers, Neil in particular, for giving me this opportunity to talk to you. I will be talking about a couple of different things, all related to the theme of probabilistic deep learning. So what is probabilistic deep learning? Well, when we use a neural network, we certainly optimize likelihoods, right? So if you train a neural network on a softmax cross entropy objective for classification, you certainly use a probabilistic model. But here I want to focus more on how to set up complicated probability distributions using neural networks, for example, for high-dimensional regression tasks. And what does it really mean to learn a probabilistic model? What's the basic assumption that we typically make? Well, the simplest assumption that we make in machine learning is we say there is a true distribution in the world, a joint distribution over all observables and unobservables, and we obtain IID samples from this distribution. And to model this distribution, we set up a family of possibilities, a family of possible models, our model class. And by identifying members of this family with parameters, we can then navigate that space of models. And really what we're trying to do is to somehow get this, a member of this family or a distribution of members of this family close to the true distribution. So in order to do that, we need some measure of how different our current candidate is and how to possibly adjust this candidate to become more similar to the true distribution. And this is only possible because we make certain assumptions that hold for all members in this family of models. So for example, we may say that we're interested in a model class where every single member allows us to obtain samples in a tractable manner. So for example, if I have a Bayesian hierarchical network, I can obtain exact samples. Or I may say I have a certain type of model called an implicit model, which I will talk about in a second. And in these implicit models, I have to be able to compute certain gradients. Or finally, I can assume that I have access to the log density function defined by my model, so the likelihood function. And for example, a model where all of this is not true is a discrete graphical model, a large-scale discrete Markov random field, right? I can either compute the log density function, the normalized log density function, or I can obtain, neither I can obtain samples from this model. Or still we can have approximate methods that somehow work with these models. And a model where all of this is true is, of course, say, a normal distribution. And so by making different trade-offs, we get access to different types of model classes, and what we want is we want very flexible model classes. And one recent innovation in the space, in particular in deep probabilistic learning, is the concept of an implicit model. And an implicit model is also known as likelihood-free model or neural sampler. Now the name likelihood-free model is quite established in certain fields, but likelihood-free doesn't mean that this model doesn't have a likelihood function. It still has a likelihood function. It just means that you don't have access to the likelihood function. So what are these models? In a very simple sense, these are deterministic functions of some random input. So you have some noise distribution which is fixed and very simple, say a standard normal in 100 dimensions, or uniform distribution in a unit cube. And you have a deterministic function g which transforms this noise into some output. So every time you put in a random input, you get one sample from this distribution, defined implicitly by this deterministic transformation. Now, if this deterministic transformation would be invertible, then through the Jacobian rule, you can just get access to the log density if you have access to the log density of the noise distribution. But in general, we want very rich functions here, say neural networks, and therefore we may map many possible inputs to the same output. And there is no inversion possible anymore, and therefore we can't compute the log density function of the resulting probability model. So how can we train these models? How can we adjust the parameters of this deterministic transformation? And recently, like in the last 3 or 4 years, there have been a couple of principles that have been discovered or rediscovered or connected to how to train these type of models. And I want to roughly structure my talk according to these principles. So one is this class of integral probability metrics, half of the talks yesterday in the GAN workshop were about IPMs. I can really recommend a kind of really very nice survey paper from Bharat Sripadumpudur on the topic. It's a class of divergence functions defined between pairs of distributions, which is defined as taking the supremum of expectations over a class of functions. So f is a function that maps from the observation space to a scalar, and you take an expectation over the p distribution, expectation over the q distribution, and you take the supremum over these. And so particular instances for special choices of these function classes yield, for example, the maximum mean discrepancy or the recently proposed Wasserstein-Ganz as successful implementations in deep learning. The next class of methods is a very classical concept. It's a concept of proper scoring rules. So this is a proper scoring rule. You can think of it as a loss function for distributions that has two arguments. It takes a distribution and a realization of the true distribution. And then it scores how well the true distribution matches, how well your proposed distribution matches the observation. And so the likelihood is the most famous proper scoring rule, but there are others. And likelihood yields a variational autoencoder as a successful implementation of a probabilistic deep learning system. And another class of methods I will be talking about in a bit more detail is so-called disco networks. And finally, we have a rich class of divergence functions, which is known as the class of F divergences, which is defined by a scalar convex function F. And the scalar convex function f, depending on the choice of the scalar convex function f, you obtain various divergences. For example, the Kullback-Leibler divergence. For example, the total variation divergence. For example, the Jensen-Shannon divergence. And each of these divergences leads to various implementations. In particular, the generative adversarial networks is a way to approximately optimize f divergences. And I will also be talking about that. Now, I wrote 3 colored boxes here, and this implies that, this is a nice taxonomy of 3 different things. It's not the case. There's deep relations between them. In fact, you can convert often, in many cases, you can convert them into each other. There's intersections. For example, the total variation divergence is both a member of the IPM class and the F divergence class. It's actually the only member that's in both class. You can take an expectation of a proper scoring rule and you get up to a constant. You get, for example, a KL divergence and things like that. So there's various relations between them. And with my group at Microsoft Research Cambridge, as well as my academic collaborators, I've been looking into all 3 classes and trying to do some research in how to apply these and discover some hopefully interesting theory about them. So the remainder of my talk will be essentially the 3 colored boxes in more detail, and then if I have time, and please interrupt me with questions in the meantime, but if I have time at the end, I have also a small snapshot of what I consider interesting research areas. And yesterday we had a very lively discussion at the Theory of GAN workshop and wild disagreement about certain things. So this is really interesting. There's still lots of research to be done. So let me talk about the F divergences and the generative adversarial networks first. Probably you have seen a slide something like this that explains the basic idea of generative adversarial networks. And I think that's part of the appeal, that you can tell a story around this class of objective functions that people have used that is very intuitive on one sense and actually has a formalization as well. So I want to repeat it here in case you haven't seen such a demonstration of the GAN concept yet. So the GAN training principle works as follows. You have an implicit distribution, which is this deterministic function, the generator function, which consumes noise and can spit out samples. And you have your training set, an IID sample from the true distribution Q. And you have a third model, an adversary, which is a binary classifier. And you hand that adversary a random sample, either from the generator or from the training set. And the adversary's job is to distinguish, is it real or is it from the generator? So the generator tries to create a high loss in the adversary, tries to fool the adversary. And the discriminator tries to distinguish the fake from the real samples. So you have 2 models, the generator and the adversary, and they are also called discriminator. They each have their own parameters, and they work against each other. The discriminator, the adversary, tries to classify well, and the generator tries to make the adversary classify badly. So this mathematically yields a saddle point problem over these two parameters in these two models, where essentially you have just the log loss applied to these two different models, to two different distributions, where one is the positive samples, one is the negative samples. And d omega is this probability provided by the adversary of this being a true sample. So this was proposed in 2014. I will mention connections to prior work. Obviously, there's lots of prior work on density ratio estimation and similar topics. But it was first put in practice with deep learning models in 2014 by Ian Goodfellow and his co-authors. And the results were so-so. So here are the results shown in the original paper. Reasonable results on generating MNIST digits, reasonable results on generating faces, and then some washed out colored blobs showing images. But it showed that the principle could work for density estimation. So there is some connection to prior work, actually quite significant prior work, dozens of papers with hundreds of citations in total, so it's not in the machine learning community, on the topic of density ratio estimation, on variation representations of F divergences, and so on. So I list a few here. The earliest reference I know of where a discriminative model has been used for estimating generative models is from Zhou and Tu at CVPR. But there's a couple of other important references, and there's a nice survey by Shakir Mohammed and Balaji Lakshminarayan that kind of tries to build connections to the relevant literature in various communities, including the ABC community. And I'm not trying to rewrite history here. I mean, there is something to be said about putting this thing into practice and making it work for deep learning models. What got people's attention, though, is not these samples. What got people's attention is when Alec Redford, a year later, produced a model that can generate images with a fidelity that people have not seen before. So these are samples from a generative model of images, the so-called DC-GAN architecture. And when you look at them, you should say, oh, they are really realistic, but has the model not just, this is a model with tens of millions of parameters, does the model not just remember the training samples, right? I could show a training sample batch and it would look probably equally good. And so how do we know that this model really has learned something about images? How do we learn that this model really has understood some semantic relevant concepts? And there's an interesting experiment that was reported in that paper where they took two random points in this noise space and then showed images along a linear interpolation in this noise space. So noise space was just a uniform distribution in d dimensions. And this is what you get. So you have two random points, these are images of bedrooms, and you get a very smooth interpolation in the semantic space of bedroom images. This was trained on 2.2 million bedroom images. And you see that objects appear and disappear, the curtain becomes a window, the perspective slightly and smoothly changes. And this shows you that it not just has remembered training samples, because if it did, you would see sharp transitions from one training example to the other training example. This really is a smooth manifold of bedroom images. And that's really interesting. There's nothing in this model that demands such a semantics to be discovered. So this was also what caused our interest in Cambridge, and we worked on trying to understand this GAN concept a bit more, and the result was a paper on a generalization called FGAN, which we published at NIPS last year. And I think it's a nice, from a theoretical point of view, it's a nice kind of summary of how we can view GANs. And I just want to briefly go through that work. So we basically extended the GAN objective to arbitrary F divergences, and we simplified the GAN algorithm as well. So how does this work? And this is really quite simple to understand, and therefore I will show you the entire derivation, which is just one slide. So we have the definition of this F divergence here, and this, I should point out, there's one very important work by Xian Longui and Martin Wainwright and Michael Jordan, who essentially use the same technique that we did, and we base our work on top of them, and we just make this connection to this literature. So I don't want to say that we invented this representation. So you have this F divergence defined by a scalar convex function F. For example, if you would choose a negative logarithm, you would get the KL divergence. And the function F has to satisfy two conditions. One, it has to be convex, and the other one is for an argument of 1, it has to be 0. And when you have these two properties, you have, as a consequence, that the F divergence is 0 if and only if the two densities match. Now, from convex analysis, we know something about convex functions. We know that every convex function has an equivalent representation called the differential conjugate f star, which is defined as a supremum over a family of linear functions. So it's simply the intuition that any convex function f can be represented as the pointwise maximum of a set of linear functions. So here's a picture, you have a convex function, and at any point you can take the tightest lower linear bound, and if you do this at every point you get a family of linear functions. And if you take at every point the supremum of this family of linear functions, you have identically represented this original function. It's just the differential conjugate representation. The variational representation of a convex function. So here's the entire derivation that we do. We take the f divergence, we put in the equivalent representation of the scalar function f, just in the supremum form. And what does the supremum depend on? The supremum depends on a pointwise argument x. So the outer integral is over the domain x, and we take it over pointwise x. So what we really would like to do is to swap the supremum and the integration. And in order to do that, we introduce a function, capital T, which takes which tries to represent the supremum over T at every point x. And this function, capital T, will be represented by a neural network. And when we do that, we can swap the supremum with the integration sign. And then the argument of the supremum distributes, and we cancel one of the q factors and introduce a p of x factor. And this has a very nice consequence that now you have a difference of two integrals, where every integral is an expectation, so you can write it as an expectation over two sets of samples. And in general, this is a lower bound, because this family of functions, calligraphic T, may not contain all functions. It may only be a subset, the functions that we can represent with a neural network. But it's a variational lower bound on the f divergence. And it has a nice linear form. It's a difference of two expectations. And note that, in particular, different from integral probability metrics, the expectations are taken over different functions. So that's the nice benefit here is having it in an expectation form immediately gives us a way to approximate that using samples from Q and samples from P. So at the top line we have something that we have no hope to evaluate because it involves a true density. At the bottom we have something that we can actually easily evaluate by drawing samples both from our model and from the true distribution. So that's really the very nice thing. Now we can compare that to the original GAN formula, and we can recover the original GAN case by making special choice for this T omega function, and then and special choice for the f function, and then we can exactly recover the GAN case. So this is a strict generalization of the GAN objective. And in the original GAN paper, they already noted that they optimize the Jensen-Shannon divergence. So now the Jensen-Shannon divergence is a special choice of this FGAL methodology. You have other F divergences. I don't expect you to read it, but it includes basically all kinds of divergences. Kullback-Leibler in both directions, Pearson chi-square, Niemann chi-square, Hellinger, Jeffrey, Jensen-Shannon alpha divergences, popular divergences. And the dual, or the conjugate representation is very easy to derive. I first did this on paper, then I didn't trust my derivations, and I did it with a computer algebra system, and indeed 3 of the derivations were wrong. So this is verified separately with 2 ways, and it's available in our paper if you want to do different divergences. So you can plot these, and interestingly, for various choices of divergences, there are various numerical difficulties. So, for example, certain divergences involve an f star function which has an exponential function, which is difficult to handle numerically. And therefore, actually, the original choice of the Jensen-Shannon divergence is actually quite nice because it's symmetric. So the two expectations are compatible on a scale sense. Okay, there are some trouble implementing GANs. I'll probably skip it now. But what you can do then, you can basically train a model. This is probably state of the art 1.5 years ago in terms of qualities of samples. This was trained on images of classrooms, and you can see, so I go through a random trajectory in this latent manifold, and I show you the samples of a GAN model, and essentially you can identify features of classrooms like chairs in the front, whiteboard, blackboards, or windows, things like that. But it's not the best model of images. Now there are way better models, but maybe 1.5 years ago it would have been. Okay, so that was on the generative adversarial networks. Let's move on to the second part, the proper scoring rules. In particular, I want to highlight variational autoencoders as a very successful implementation of probabilistic deep learning. So what are proper scoring rules? A proper scoring rule is a function of two arguments, density or distribution, and a realization of the true distribution. If you take the expectation over the second argument, using the true distribution to take that expectation, then you can get a divergence function between two distributions, P and Q. And a proper scoring rule is a scoring rule which has a property that it is minimized when these two arguments are identical. So when you have the true distribution, you have the minimal possible scoring rule. Sometimes in the literature the direction is reversed, so the high score is good, but in machine learning we try to think of losses. So for the discrete case, where P is a distribution over discrete outcomes, there's a complete characterization, the so-called Savage representation, which completely characterizes all proper scoring rules. But for the continuous case, as far as I know, that's not the case yet. However, there are multiple possibilities, and the most popular is the log likelihood, where it's just a point-wise log density evaluation. But there are other scoring rules as well. So a variational autoencoder is a way to do approximate maximum likelihood in a deep generative model, and it has a couple of ingredients put together in a very clever combination. So first off, it is a model. The variational autoencoder is a generative model. And the model is not new per se. David Mackay was looking at similar models in the mid-90s. It is simply a hierarchical model where x is observed and z is a latent variable. And you have a conditional distribution of x given z and theta parameters, and you integrate that over the unobserved latents to get a marginal model over x. So think of x given z and theta as, for example, a normal distribution, and then taking an infinite mixture of normal distributions. So a single normal distribution is very limited in its expressivity. An infinite mixture of normal distribution is very, very flexible density model. So you can think of this as an infinite mixture of normal distributions. And we will use neural networks to map z and theta into the parameters of a normal distribution. So this obviously is intractable, but what we would like to do is to do maximum likelihood. So we can just start writing down the log likelihood function, the marginal likelihood that we want to optimize over the parameters, and then do what we used to do since the late 90s is variational inference in machine learning. We approximate this likelihood with a lower bound. So we write down the marginal likelihood, just the definition of it, and then we introduce a new density Q. Nothing has changed. We just introduce it with suitable support. We swap these factors. Nothing has changed. It's still an equality. And now we can write it as an expectation over Q. Still nothing has changed. And now, whenever you have log expectation of something, you can apply Jensen's inequality, swapping the expectation and the logarithm to get a lower bound in this case. And this term can be rewritten in an equivalent form by splitting off the second ratio, and that's a KL divergence. So now we have a lower bound on the marginal likelihood, which involves a new distribution Q, which is a variational distribution. So we want to optimize it to find the tightest lower bound. Now this is great, this is variational inference, and for variational autoencoders this does work, but it's horribly slow. And the real breakthrough in the variational autoencoder paper is to consider something called the recognition network or the inference network. Actually, it has been invented a couple of different places under the name of amortized inference, memory-based approach, informed sampler, various different approaches, which tries to make these variational inference much more faster. And the basic idea is this: if you have the variational approximation that I just showed you, you have one variational distribution for every data item. So if you have a training set of 100 items, you have 100 variational distributions, because you need 100 lower bounds on the marginal likelihood. And you adjust each of these parameters separately by optimizing this marginal lower bound. Now, the idea of an inference network is to say, actually, let's couple all of these together. And we do this by a neural network. And the neural network consumes a data item X and has some parameters W, and directly gives the parameters of a variational distribution. So instead of optimizing something with an iterative procedure, you have a single feed-forward neural network that gives you a variational approximation. And so when we plug this into the derivation, nothing changes except that we add into this Q distribution, we always add X and W. The result is exactly the same, but now we have coupled together all the variational approximations. So from a single sample, I can learn about all other samples. I can modify the variational approximation of all the other distributions, all the other samples. And this motivates the name of the variational autoencoder, because you can see these two models, the Q model and the decoder model, you can see them as stacked together into an encoder step, which encodes a sample X into a latent representation Z, and then a decoder which takes Z and decodes it into a sample X. Now after training, you can throw away the encoder and you have a generative model. Or you can keep the encoder and you can do inference in both directions. And you have the single objective function which you want to maximize, and this is very compatible with deep learning. It only involves expectations and some parameters, and it doesn't have all the difficulties of GANs. So it's just a maximization problem. You can look at the plots. And most of all, it's fun to use. So here's a fully self-contained example generating human post data. And probably you can't read it, but this is the entire encoder, this is the entire decoder, and this is the objective function computation. So using modern deep learning frameworks, you can implement this in literally 20 lines of code. And this is the first try of generating human post data, absolutely unaligned data, so you see the person sliding a bit. But it learns a manifold structure of the 60-dimensional space, so it outputs 3D coordinates of all these joints. And I plot a linear trajectory in the latent space and show you the interpolations of the mean. So as a generic density model for high-dimensional data, it is really quite nice. Okay, so what are the problems with VAEs as of today? Basically, there are two. One is you have the variational approximation, which may be poor. And on the other hand, you still have to specify this parametric likelihood model, the conditional model. And that forces you to choose a parametric distribution. And of course, you could say that, okay, a normal distribution is not so limiting. If I take a mixture of normals, infinite mixture of normals, it's very expressive. And that's true. But we see there's a huge influence by making that choice. So that tells us that actually it matters quite a lot, and there are not so many parametric families available. So a GAN model avoids that difficulty. And these difficulties manifest themselves if you do, so if you take a test image, you do a reconstruction, you get sort of a reasonably blurry reconstruction, and the blurriness comes from both the variational approximation and from the poor likelihood, conditional likelihood that you have to write down. But you can do interesting things like making people smile and stuff. Okay, so what can we do? We can look at this autoencoder viewpoint, and we can say, okay, let's improve this variational approximation a bit. And actually, people have tried quite a bit. So these are existing work of trying to improve the variational approximation and variational autoencoders. And we add one line to it, the adversarial variational Bayes method. Actually, it's not, we didn't add only this one line. There's actually 3 related works which do more or less exactly the same at the same time. So it's a very contested field at the moment. I just want to briefly talk about this. Around 12 minutes left, probably. Let's see how it goes. So what we are going to do is to use implicit models as variational families. And this is joint work with Lars Mischeda and Andreas Geiger from MPI Tübingen. So what do we currently require from this Q model when we maximize this elbow objective in the variational autoencoder? Well, we require 2 operations. We need to draw samples to approximate its expectation, and we need the log density function of Q. And we want to get rid of the second assumption. And this gives us access to richer families of functions, in particular these implicit models, which take some fixed noise distribution and transform them in a nonlinear way into rich and complicated and multimodal and whatever heavy tail distributions we want. So here's the high level idea. The paper is on archive, the draft is on archive, you can actually read a lot more details there. We have these elbow objective, we write it slightly differently by expanding the KL term, and then we identify the log density ratio that appears here, where we need the log Q. This is the only part where we need the log density of Q. And we introduce a variational function T which takes both x and z, and this variational function tries to approximate this log density ratio. So, in order to get this function t, we set up a separate optimization problem, which has the same structure as a GAN optimization problem. And what we can show easily is that this optimization problem has, as an optimal solution, the precise log density ratio. So this is not like difficult to show. But what this allows us to do is to just say, we take the elbow objective and replace this difficult log density ratio with t star. So now we no longer need the log density ratio, we only need t star. And note that in this optimization problem, we only need to sample from Q. We no longer need the log density of Q. So we get two optimization problems. This is an instance of multi-level optimization, as David Pfau yesterday has mentioned at the workshop. This is different from the saddle point viewpoint of GANs. This is more richer. This is a multi-level optimization problem, where we have two related optimization problems which are coupled to parameters C. So we solve these problems simultaneously with a GAN-type algorithm. The algorithm is relatively simple to implement. It's just taking 3 gradient steps. It's something you can very easily implement using any modern deep learning framework. And we have more details in the paper pointing out connections to other related approaches and some theory regarding the approximation. But going to the experiments, this actually works. So this is an ICML paper. ICML papers don't need MNIST experiments. NIPS papers do. But still we have MNIST experiments in this paper. So because many other people have worked on MNIST for variational autoencoders just to see what the elbow looks like. It's probably hard to read from the back, but 3 conclusions. One is that our model achieves state-of-the-art elbows, and we verified that separately with annual importance sampling. Going to high-dimensional spaces helps, so the capacity of this latent vector Z matters. And we are state-of-the-art compared to a recent work called Householder Flows from December last year in terms of the elbow objective. So, now I have 9 minutes left. Okay, let me see how I structure this. So, the integral probability matrix is a classic concept, and I really can highlight Barat's paper again here. It's a very nice summary of various IPMs, where if you compare that to the objective that we had for GANs, we have the same function appearing here. We don't have this f star function. We always have the same function f appearing here. And so the only freedom that we have in this form is a choice of function class calligraphic f. And that gives us different integral probability metrics. So for example, if f is a unit ball in a RKHS, then this supremum can be solved analytically, and in particular it is just a difference, it's a norm of the difference of 2 kernel mean embeddings. So by the choice of kernel you determine the RKHS, and that determines in closed form the maximum mean discrepancy, or kernel maximum mean discrepancy. And you can estimate that. The MMB square can be estimated unbiasedly using a simple formula. So you're just taking certain sums of kernels. And that has been used for learning deep generative models. It has been used by Yujia Li from Rick Zemmel's group and by Carolina Tsugate from Zubin's group 2 years ago. And it has also been used by Douglas Sutherland and Arthur Gretton and others for model criticism. So even if you don't want to train a generative model, maybe this is a good way to look at and evaluate the performance of a generative model. However, right now I think it's fair to say that the performance of these models are not at the state of the art in terms of GANs or variational autoencoders. So these are MNIST samples and simple face samples, and they visually do not look as nice. And so it's an open question whether the MMD line of work, by clever choice of kernels or by learning the kernel parameters, can be pushed to the same state as other models. Now, one brief work that we did, which is essentially just an interpretation of the kernel MMD approach, coming from a slightly different angle, coming from the angle of proper scoring rules, is with my student Diane at Oxford. This was also a NIPS paper last year. And in the paper we describe it in one way. I would like to describe it in a very different way, which is trying to convince people who right now don't use probabilistic models to give probabilistic models a chance. And here's a very simple pitch for that. So say you want to solve a high-dimensional regression problem. So you go from some sample space X to some target that you want to regress to. And right now you use least squares regression or some other kind of simple regression model, or decision tree, regression tree, or something like that. And what you really want to do is you want to represent uncertainty, predictive uncertainty over Y. So you really want to regress into a distribution, a family of distributions defined over the possible outcomes. So how to do that? Well, right now you have a regression function which takes some measured covariates or features, the blue stuff, and tries to regress a target. And probably you use a principle like empirical risk minimization for that. So you minimize some expected loss over the true distribution. Now here's a simple recipe how to convert that into a probabilistic model. You attach some noise distribution to your inputs, just sampled from, say, uniform distribution. And then you take the expected loss over this noise distribution. Well, if you look at this empirical risk, any good regressor should just try to ignore the noise. It's uninformative about the prediction target, right? So a linear regressor will try to set all the weights for these dimensions to 0, hopefully. So in order to prevent that, in order to force the model to somehow use that noise, we add another term which says, if I give you two different noise realizations, I want you to actually maximize the loss between two prediction targets. So you pass through different noises in your regression function, and you have a negative sign here, so you try to penalize models that output always the same thing. Now you can interpret this very simply as minimize some expected loss minus diversity. And the coefficient 1/2 is actually important here. So intuitively this is plausible, right? Make predictions which have low loss, but keep them diverse somehow. But is this a sound principle? And actually it turns out it's a very sound principle. This, for certain choices of loss functions, this yields a proper scoring rule. So it's a perfectly valid principle. If you're happy with the likelihood principle, with likelihood as a way to estimate parameters, you should be happy with that as well. And you can get very rich probabilistic models. If F is a rich function class, such as a neural network, you can get very rich models out of that. And so there's two connections. One is to the scoring rule literature. There's a very nice paper from Tilman Gneiting and Adrian Rafteri in JASA 2007, which basically shows that for this choice, this is a proper scoring rule, and there's a concept called the energy statistic in statistics, which is related to that as well. And then there's also the link to the kernel MMB objective, and it's known that, for example, if you choose a certain Euclidean norm to the certain power, fractional power, then this is also a conditionally positive definite kernel, and you get like a nice proper scoring rule. So how did we use this in practice? What's the application? And we use this for hand pose regression. So you observe a hand image, and we take a convnet, and then we attach some noise vector in the middle of this convnet, and then we output deterministically one hand pose. So depending on the noise vector, we output slightly different hand poses. We're super efficient. At test time, we can just evaluate a batch of like 10 different noise vectors, and we get 10 exact samples from our conditional posterior. And the objective is simply empirical loss minus this divergency loss. So here are some examples. There's numerical experiments in the paper, of course. But for simple poses, there's a slope predictive uncertainty, and for complicated poses, there's high predictive uncertainty, just like you want. So finally, I have 2 minutes left, I think, and maybe that's not enough to discuss current research areas, but I can give you a brief view on what I consider really interesting. So we want to use GANs as building blocks. So deep learning models are essentially like Lego architectures. We assemble layers in a very flexible way, and usually this works quite well. And there's a diffusion of technology across different communities, natural language processing, computer vision, machine learning, speech, because of this Lego brick architecture. So somebody invents a certain recurrent neural network layer in a natural language processing community, and I can use it on the next day in my vision model or in my speech model. So we want to make GANs equally reusable. GANs should be Lego bricks. And that can appear in multiple cases, so we want to use it as a model component to have rich conditional distributions, for example, in a hierarchical model. There's recent work by Dustin Trun, for example. Or we want to use it as regularizer. We want to compose this in any arbitrary way we want, and we want to expect it to work. So we're not there yet, but this is a trend I see. And we can use it for variational inference, for example, like I showed. So one big issue in GANs is the stability argument. It's difficult to train, and a dimensionality argument as well. There may be a dimension mismatch. And let me explain to you briefly what I mean, and then I think I will conclude the talk because we want to leave some time for exciting discussions. So in a typical application of GAN models for images, something is deeply broken. We take a 100-dimensional noise vector and we map that into a 30,000 dimensional space if we have 100 by 100 by 3 color channels images. So what we really try to do is we wiggle this line of low dimension into this high dimensional space. And the support doesn't even match. So the true distribution over images has some dimensionality. There was an argument yesterday. I believe it has full dimensionality. I've worked on image statistics for a long time. But, sorry, I had to say that. It was a very, very heated argument yesterday. But anyways, there is a dimension mismatch. Maybe we can agree on that. So we don't know the dimensionality of the true manifold, and therefore we probably don't have the right support. So that means there will be a realization, which is where our model says there's a zero probability of that happening. And that leads to problems and stability issues in training GANs. And so there's two solutions, one solution to this, which have been proposed independently, actually by Ferenc's group and by Martin Ajowski and Leon Boutou, which is to convolve the resulting density. You see, there's a convolution happening. Convolving that with a kernel to restore the full dimensionality, and that seems to help empirically, and it's probably one of the most easy and successful recipes to stabilize GANs. And I think I'm out of time. I have a few more slides, but I am out of time. And so let me actually see if I can jump to the final talk. So finally, I think probabilistic deep learning, there are many exciting methods, lots of work to do. Actually work on many levels, theory, applications, making these things work. It's a great progress in the last 3 years. Actually, it's really exciting. And it's not just generative models. It's also just discriminative models, right? So whenever you need a conditional distribution to make good predictions or generative models, both are included in these methods. And the current challenges mainly related to training and stability, and also how to structure these latent representations, how to get structure in the latent space that is suitable. So that's kind of the interesting bit. So with that, thank you very much for your attention.
Questions, Ralph?
So, nice talk. So one question I have is, by talking about probabilistic deep learning, it seems that a lot of times the neural network or deep network is sort of thrown as a nonlinearity. But is there any guidance on how much nonlinearity and how many dimensions you have, how you structure the nonlinearity that comes from the probabilistic model? I think that's one of the nice things in the graphical model. It's kind of prescriptive of the generative process of data.
Right. I think there's some tension, right, between hierarchical Bayesian networks, for example, really satisfying way to think about the model in various components, how to think about individual things, and how to really structure them. And maybe at some point you really need a complicated distribution. Maybe there you're willing to plug in a deep network or something. And so in principle, these are compatible. And it also depends on the availability of data, right? So some people, for example, in the computer vision community say, we don't want to learn physics, we know physics, right? So let's build in physics in our model. But actually physics are very regular laws, right? So the model, a flexible model with enough data should be able to discover them first thing, right? And then learn all the complicated things which are based on top of physics. So I don't know. The answer is, I don't know. Right now I don't see a consensus or kind of a guiding principle how to structure these models. It seems that it's helpful to allow for certain layers that can be kind of like ResNet type layers that can learn to completely switch off to just become an identity transformation. So then you at least have some guarding principle in your model that it can become very simple, right? You don't want a model that has to use nonlinearities in every step. But other than that, I don't really know.
And then we'll do both.
So I have actually two questions. One is, there is this work on differential geometry of probability distributions.
And the Kullback-Leibler divergence there seems to have a special role in terms of the connection of the Riemann geometry. So do you see some support from that work for what you are doing? Because you are proposing many different functionals which seem to have good properties, and the good properties are basically shown by eyeballing the results.
Right, so that's the problem. I mean, okay, it's a bit loaded question, right? There's so many components in that question. I agree the state-of-the-art evaluation, that was another big component in the discussion yesterday at the workshop. The evaluation of these models, except for the variational autoencoder, which has a nice likelihood bound, the evaluation of GAN models is deficient at the moment because we look at samples, right? And humans are good at judging certain properties of samples, but bad at judging other properties, like whether we get the distribution between different modes and so on. So now for the information geometry argument, actually I think a big part of that is what you want to do with your model. So if your model is misspecified, which is usually the case in practice, right, you suffer some loss or some error due to the misspecification, and then the different choice of divergence function actually has a huge influence. When you have model classes very rich and you have basically too few data but a rich enough model, then the divergences don't have such a strong influence, because with enough data, as data accumulates, you're going to agree on the same solution. So the influence is strongest when you have misspecification, and this was a starting point for our work on disconnects, where we start with a task-specific loss. So when you know how you will use your model, in particular to make decisions or make certain point estimates afterwards based on your density, then you want to use that knowledge to inform your choice of divergence function. And I think actually I may have a slide on that. There is some work from Simon Lacoste-Julian as well. Let me try to find it. So let me see. So here we are outside the setting, okay, and we have different divergences which project differently on this manifold. And so Simon analyzed this on when we use the variational inference procedure, we essentially try to do something similar. We have a distribution Q, which is the exact model distribution that we want to approximate in a model, and then we use variational inference. And we use variational inference like the I projection, the reverse KL divergence, to get one approximation to the distribution. But is this really the good one? Should we not maybe project in a different way, right? So it's a similar problem now for variational inference. And if you know your loss function that you will eventually use in a specific task, you can do better, because you can essentially do the right trade-offs during inference time.
And just a quick answer for clarification. You argued that the smooth transition in your linear interpolation is an indication that the network has understood semantic content.
Right.
Isn't it exactly the opposite? Because objects have an entity, and if they appear and they disappear, it should be disruptive. And what you are basically doing is blending computer graphics in a way that it looks nice, but it has not understood the semantic content of an object.
There's this old question in computer vision, maybe you know this, what is a chair, right?
No, but and you get heads with 4 ears and 4 noses and 2 mouths.
I don't.
And they look very smooth.
Well, it's easy to criticize the artifacts, but because you criticize these artifacts like whatever, 3 years or 4 years or how many years, I think it's also easy to lose the main breakthrough which has happened, which we did not have models which can generate these images before. So we certainly can generate some properties of images which make them maybe disturbing, because the properties that don't match yet, especially for faces, we are highly tuned, right? They stick out even more, and we complain about them. But I think the general progress is very exciting, and my samples did not look very good. If you want to see, probably the best samples is from Jeff Clune's paper on plug-and-play generative networks, and he has beautiful videos where he flies through a manifold of volcano images, and it's just amazing. I mean, it's just literally you see a smooth manifold of volcano images coming out of this model, and it's kind of very interesting how these models achieve this. So I agree there are limitations, but
so Aldo, was yours a follow-on or
Follow-on?
It's a follow-on. Well, I'm overrunning considerably here, but I'm relaxed about that. One second.
So just to turn also Joachim's comment in your claim around. So if you're saying that the smooth transition is also a reflection of semantic understanding, then are you suggesting that if you look into the model's internal space, that there should be a topographic organization that reflects different regions, reflecting different semantic meanings of bedrooms?
Yeah. Certainly, I can show you actually a slide which I briefly flashed maybe. So here's an example of some experiment that tries to understand the latent structure of the latent space in a variational autoencoder model, but it's similar in a GAN model. So what we did here is we had face images. We trained a variational autoencoder purely unsupervised. And then what we did is we take 150 images with sunglasses, 150 images without sunglasses. We take the centroid vector in the latent space of each of these 150 images, and we just have the difference vector. And now we take an image of somebody, where is it? No, sunglasses, it's smiling, for example, smiling and non-smiling. Two centroids, difference vector. We take an image of a person not smiling, we add this difference vector, and we make that person smiling. And so that reveals that there is what people call in vision linearized semantics. So you have some linear arithmetic space where you can do certain transformations which are reflected in a semantic way. Now this is a vague concept, right? It's not like if you pin me down and say, oh, but you want to quantify this, I would be hard pressed. But it's interesting, and that was what makes these models exciting, in that they just somehow discover these latent representations. This must be a very compressive way to represent information by organizing the latent space in this way. So people are trying, and many people probably try in a better way than we did, but we're trying. Yeah.
But
yeah, so I have a question about, first of all, thank you very much for a very nice talk. I have a question about the, so you talked about the variational bound and also about this multi-objective idea. And both of them involve some distribution that you have to optimize, or something that you have to optimize, right? Is there any, can you say in any sense that one approach is better than the other?
I think it's too early to say. I had a discussion.
No, I mean mathematically.
Mathematically. Well, certainly with a variational approach, you need to make, with a variational autoencoder approach, you need to make an assumption about your variational distribution family. And usually it's a quite simple family. So that may be limiting. Whereas using these implicit models gives you more freedom. You can just add capacity to your neural network, and the distributions can be more richer and richer. So yeah.
But you can also do variational. You can also make it. I mean, you also have the.
You can also, and people tried, but and we use implicit models for variational distribution. So in a way, we provide the closure, right? The connection to GAN. So, but it brings its own difficulty. So I think theoretically, there's not much one can say about whether some approach is universally more expressive or similar things. I don't think that's necessarily the case. I think. A few months ago, I had an interesting discussion with David Devenot, who said, "Why isn't everybody using variational autoencoders?" Right? See, but now he uses GANs himself. So I don't know. It's kind of a very developing and.
Okay, thank you.
Really, one last question.
Yeah, I hope it's going to be quick. You haven't mentioned the learning times for this, the training times.
Right.
Can you give us an estimate?
Yeah, so we are fortunate enough to have good GPU cards in Cambridge, but so you can train reasonable models. Say for this images, this is a Celeb A image set. You can train 4 or 5 hours. You can get very reasonable models on a single GPU. So and if you don't have a GPU, it's easy to get now a cloud server with a GPU. So it's literally just a few clicks away. So it's not that. There is some intrinsic difficulty getting access or to time but it slows down the experimental feedback. So that's one of the big limitations, right? For the big models, maybe you take a few days to train these things, and then it actually allows you to do only so many cycles of experimentation. Great. I think I run way over time, but thank you for being so.